Hello everybody. We're still talking about the numerical integration and the analytical integration, and we will now see the other function that we can use to do the analytical integration. So in the previous video we saw how we can deal with some other or some simple functions like these, which has a function of a variable, and you want to integrate or integrate this function. So you can simply do it because you have using the end function, because you have all the variables on the other side. But in a case like this, when you have an equation like this, we saw that we will not be able to do this using the end function. So we need to first separate the variables, and then we will end up with a function like this, which is ln y equals all these kind of stuff, and then we will end up with a function which is y on one side equals this expression. And actually, there's some important terminology that we need to agree on. I think they're pretty famous and well known, but just in case any of the audience is not familiar with them, we will be on the same page, which is the dependent and the independent variable. When I write an expression like this, what I have here, it means that the y changes with x. So it can be concentration with time or with space, whatever. So this is the independent variable. It changes independently. It doesn't matter what is the value of y. And y is dependent on x. So as the value of x changes, the value of y changes accordingly. So that's why we call this the dependent variable, and this is the independent variable. And you will end up with an equation that has a constant, and to be able to get the constant you need some information, and this information can be what we call a boundary condition or an initial condition. Both are kind of similar, but the difference is that and they both relate the dependent variable to the independent variable with some known information. So I know at specific time I know the concentration, or a specific distance or location I know the concentration, or whatever the variable that is dependent. But when it is a function in space, or the independent variable is a function of space, it's like distance, like something like this, we call it a boundary condition, because it is usually at the boundaries of the geometry. So we call it a boundary condition. And if it's a function of time, then I know at a specific time, I know some kind of information about the pressure, the concentration, whatever. I call it an initial condition. And we call it initial because generally it is at time equals 0. I know when I start the process, I know the information about the system. So they take the shape like this. You can say at time equals 0, concentration equals 10, or concentration of 0 equals 10. You can put it as x equals 5, pressure equals 20, and x is a distance, so it's going to be p of 5 equals 20. Sometimes you can get it as a differential form. So you know at time equals 2, for instance, the dy by dx equals 0. So you can write it like this: dy by dx at t equals 2 equals 0. It's not 10, it is 0. Sorry. So we need to understand these concepts well, because when we go to the Matlab and start to do this calculations or the integration on Matlab, we need to know that these information are important to give to Matlab. So let's go and see what we have here, and let's see the function. So the function that we use is called dsolve. It's used for many things, but we will just focus in this video on just solving differential equations analytically. Again, we will need to do the sims thing. I need to just clear and you'll see. We need to define the dependent variable and the independent variable. We need to define the equation that we are going to use, and the boundary or initial conditions that we know. And that's why the equation will need, or the function that we are going to use now will need more information than the end function that we used before. So first I need to, let's say I have an equation like this. I'm gonna just put them side by side so that we can see we can see them well. So I have now in this equation the y is the dependent variable and x is the independent variable. So I need to define these dependent and independent variables in the symbol definition here. So I have to make it y as a function of x. Here you'll see that he understands that they are two separate variables, but if you don't define it like this, if you just define this as y and x separately, uh, Matlab will not be able to do or the dsolve will not understand that this is a differential equation. The equation has to be defined in a way which is not very straightforward, but it is easy to understand. You have to say that diff, which is, it means that it's a differential equation, and or the different the d by d, which is this. So I have to define the dependent variable and the independent variable. So I'm gonna do it like y and x. For now, I'm just gonna keep it like this. So this means this. Okay. So what I wrote here equals the dy by dx, and I'm gonna use a very simple equation. I want to make dy by dx equals to x. You have to use double equal. It's not single equal that you can use. So this is an equation. He says that it's a symbol function, and the y is a symbol function, by the way. So it's not just a symbol. He understands that this is a symbol that symbolizes a function. And now to get the integration, it's gonna be dsolve, and the dsolve will require an equation which is this, and the condition is optional, so you can put it without the conditions, and you will see it's giving you a symbol or a constant here. So this is the first thing. You can do integration for second order derivative. So let's say this is d 2y by dx squared. So if you want to make it like this, just put 2, and you'd see the equation when you do the integration is getting longer because you're integrating it twice, and you have here two constants. So you can here put the order of the integration here, and you have to define the y and x, the independent and the dependent variables, the dependent first and then the independent variable. Okay, so now let's see the next thing is how to define the boundary conditions. Let's go for and of course you can put everything in one function. You don't have to separate them. So for instance, I can do integration like this, and I'm gonna say that this is dsolve, and this is the diff y by x equals let's say x, and put and this is gonna be the same as what we did here before. So this is the same equation as this. You can add the boundary conditions here after the differential equation. So I can say that y of 0 equals 1, for instance. So this condition means that y of 0 equals 1, that at x equals 0, y equal 1, which is exactly something like this. Okay, so this is the boundary condition, and you have to put double equal, and you'd see that this is exactly the same equation, but you have this as 1 instead of just a constant. You can put it as 5. It's gonna be 5. Because this is the value of the constant. You can change it like y of 2, and the equation would be different because the substitution is different now. And now let's see if I have two boundary conditions. You would understand that the initial and boundary conditions, the number of conditions equals to the order of integration. So if I have second order integration, I'd have two constants here. If it's first order, I have only one. So if I say, for instance, this is a second order integral, so I should have two conditions. Even when I have one here, I still have the two not well defined. So to get them, I should put two conditions, but the two conditions should be in the same slot in the function. So again, um, I'm writing the equation now, and this should be the condition. So if I have two conditions, I should put them together in a matrix. So in this matrix, I put y of 2 equals 5, and I would put y of 0 equals 1, for instance. Again, I should have 2 equals. It's very confusing. So you see that this equation is exactly like which one, like this. Okay, so I have c4 multiplied by x and c5, so c5 here and c4, which is 4 over 3. So it's working very nicely. You can try different things now. For instance, you can try without boundary conditions, try an equation of y, or let's try the equation that we just wrote here, which is 2x power 2 without boundary conditions. I make it 2 multiplied by x power 2 multiplied by y. So it is c1 multiplied by exponential 2 x power 3 divided by 3. So it's giving the same answer. Again, you can put some boundary condition, which is y of 1 equals 1 for NSO, again double equal. So it's giving you the equation with the values now. Okay. One thing that is very nice to notice is that in integration, sometimes it gets very complex. So if you go for second integral, it's gonna be very tough. So if you write the equation like this, I'm gonna make it pretty. You see that the equation is horrible. You have Bessel function, and you have like kind of very tough equations here. And if you make it, I'm sure that if you make it a third order, he's not going to be able to do anything about it. He's now busy, and he says that it's empty sums. I cannot do anything for you. So this is how to write the equation, how to do the integration. One last thing, if you have an integral or a boundary condition which is like this, how can you define it? In this case, you have to define it in a different way. So you cannot just write dy by dx. So you have to define the dy, which is the diff y with respect to x. So this is the thing that you have to define first, and then you can put the dy in the equation. So I'm gonna get the integration for, let's put it as, or no, not this. I need to have some second order integral for a simple equation. Yeah, so an equation like this. So I'm integrating the dy by dx, or the 2y by dx square equals x, and I have a boundary condition here, and I want to make it dy of 2. So I have already defined the dy, which is the dy by dx. So when I write dy of 2, which is dy by dx at x equals 2 equals to 5. And now you can get the solution as we see here. So it works for both. Again, just to show the difference, if I don't put it like this, it's going to give a different solution because this is a different boundary condition. So it works nicely, and it saves a lot of time if you're gonna do a lot of integration steps. But as I told you before, the analytical integration is not always possible, and that's why in the next videos we'll see how we can do the numerical integration to be able to get outputs of functions that are not possible to integrate analytically. So I'll see you then, inshallah. Goodbye.